I'm James. This is Dan, and we're going to be presenting a little research project or research presentation on a project that we both did where we implemented some cool crypto algorithms on software and hardware. First, a little bit about both of us. Me, James Southcott, first thing, big Jesus guy, and I just finished up an internship at Apple Information Security. I'm a third year honors, bachelor's, master's accelerated cybersecurity student. I'm originally from Rochester, New York, about 20 minutes west of here, a little town called Churchville. Go Bills. I'm the captain of the CCDC team. We have our information session next Friday at 4 or 5 in Golisano 2400. CCDC is a lot of fun, really close team. You guys should definitely go to that info session. I'm also the Red Team Chief. I recognize a lot of you from Red Team recruiting the other night. Definitely come this next night. It's going to be a lot of fun. We're going to do some live vibe coding, and we're going to have a lot of fun. I'm also on the club volleyball team. I play a lot of other sports, golf, hockey, tennis. We have a we have a bunch of intramural teams. We have an intramural hockey team and an intramural flag football team, and we need people for the flag football team. So if you are looking to join a flag football team, please join. Camden, yeah, please. Chase, yeah, I know you want to play flag football. So we need people for that. So please ask us if you're interested. I listen to a lot of country music, and I like to go line dancing pretty much every Thursday and Saturday night. You can find me at Nashville's. And I'm also a big Chick-fil-A guy.
Unbelievable. All right. Hey, everyone. I'm Dan LaChance. I'm a third-year cybersecurity major, no longer computer engineering minor. Many of you would probably know me. I'm the president of the club. And this past summer, I was at Microsoft doing an internship in cloud security research. I love driving. I'm an avid hiker, so I went to, I think, like 13 national parks this year. So there's just like a couple of them up there. And then, yeah, I like to rock climb. I love all you can eat and go Bills.
Go Bills. A brief overview before we get into the presentation, because I know there's a lot of first years here. So encryption simply means to take plain text or text that is human readable and convert it with an encryption key and an encryption algorithm to ciphertext, which essentially means text that is not readable by humans or computers. And there's two different ways we do this. We have symmetric ciphers and asymmetric ciphers. The symmetric cipher, the algorithm is going to use the same key for that encryption and decryption process. Asymmetric encryption uses two different keys for the encryption and decryption process. I just wanted you guys to be aware of that because we're going to be using those terms throughout the presentation. On the asymmetric side, I don't think we're going to get into how that actually works. It's just a whole lot of fancy math. It's actually quite simple, but it's kind of out of scope for this presentation. So what did me and Dan do? It started with, that's definitely me and Dan in crypto. It's totally not us at Yosemite this summer. So we were sitting in crypto, and we're learning all this cool stuff. We learned about DES, we learned about AES, and we learned about RSA, and we're like, hey, what if we implemented this ourselves by hand? Because we learned about how they were creating these algorithms, and they originally created DES to be efficient on hardware implementations. And as more and more software on hardware became prevalent, we needed a software efficient implementation. And there were also other problems with DES. So they created AES. And then they also needed to solve the key transport problem. So we needed a asymmetric algorithm. So they created RSA, which was also efficient for software implementation. But we didn't fully implement any of these in class. So me and Dan had the crazy idea of what if we fully implement all three of these algorithms on hardware and software? So that's what we did. A little bit about these three algorithms. DES was the first one to come out. It's a symmetric cipher, a 56-bit key. It's a block cipher, so that means it, let's say you have let's say this is some text. It'll split them up into equal size blocks and encrypt them one block at a time. So each block is 64 bits, which was too small, which is why one of the reasons why AES was created. It's a Feistel structure. Dan will talk a little bit more about that. And importantly, it was efficient for hardware implementation. However, it wasn't efficient for software implementation, so AES was created. It's also a symmetric cipher, 256-bit key, so it can't be brute forced. It's also a block cipher, but it has a 128-bit block. The bigger the block, generally the more efficient and more, I guess, just, what's the word, efficient is it's going to be, because it's going to do more at a time, and you don't have to run through that whole encryption process more times. It is not a Feistel structure, which is important, and it's efficient for both hardware and software. Finally, there's RSA, asymmetric, so it uses two different keys. The keys are massive, 2048 bits, and it's also efficient for software implementation.
All right. Before we get started on this actual hardware, I thought it would probably be important to introduce what a hardware description language is. So this is actually not a programming language. Every computer engineering professor will scream at you. I'm just kidding. They're just gonna like be upset with you, and they're gonna correct you. That they're actually very different from programming languages because they actually define hardware. So like circuitry, like logic gates, so like and or NAND, those kinds of things. And it defines how each of those or how a design will get implemented into an actual like PCB, which is a circuit board. So primarily the ones that are used right now are VHDL and Verilog, if you've ever heard of those. And then they define hardware specifications, and there's in that compilation process, there's like really three parts of the compilation process, but the primary two ones that I'll talk about are synthesis and implementation. So in the synthesis, what you're doing is you're pretty much just like compiling the design into like a generalized form that can be implemented onto any hardware, and then the implementation is very like a layout very specific to the field programmable gate array, which is like a programmable hardware device where it actually like changes where power can get routed, and you can actually implement physical and OR gates into like the actual transistor level hardware. So yeah, that's what a hardware description language is. So what can you actually do? So I thought that this would be useful, like the comparison of what a programming language can do versus a hardware description language. So hardware description languages are very limited, and they're oftentimes extremely difficult to work with. So in programming languages, you have very nice things like accessible arrays. In hardware description languages, you can't really have those because what are you going to do? Have a variable? That's not possible. You can't just like access some memory location because this is all just like wires and transistors. So that's not really a possibility. So you have to like physically hard code every single array that you're going to be accessing. And then if you have like a value like a 0 or a 1, every single one of those values in the actual board array is either going to be like it's going to be wired to power or wired to ground. So that's your 1 and your 0. And speaking of variables, obviously you don't have any of that. You have signals, so it's effectively just raw binary. It's power and then no power. And there's like some more that you can get into that, but effectively just think of it that way. Then there's like inputs and outputs. So this one is like kind of easy to think about. That's effectively just what pins are. So like that's just where you would plug into for like your actual hardware implementation to either get power in or get power out. Then there's methods. So instead of having actual methods, so that's like, think of a method like you're compartmentalizing code and you're making it usable multiple places. That's kind of how components are treated. And so components are like a smaller design that will actually get compiled and built onto into multiple locations on that in like your wider design. So one note I also wanted to say is you're working with like raw binary on every single one of these things. So it's pretty important to like keep track of what you want and like your expected outputs, and that they're not changing too much. But since you are working with raw binary, you can encode like ASCII text and encrypt that kind of thing using algorithms like DES. So oh, yeah, I forgot I put this on here. Also, what is a signal? It's physically just a wire, but you can just like treat it as a binary string. So say you have like 8 different bits that you're trying to transport from one location to another. Effectively, what that's going to do in like the compiled hardware design is it's just going to have 8 wires from point A to point B. And so if you see like this standard logic vector 63 down to 0, that's effectively just 64 wires going from one location to the next. And then 32, it uses like the 31 down to 0. That just means 32 bits, but it just is defining how you're going to access each one of those bits when you're actually like programming this FPGA. Okay, so if you don't know what DES is, it's a 16 rounds of it's a 16 round encryption algorithm where it primarily uses there's like 3 different stages. So there's permutations, key scheduling, and then the F function. And this is kind of how the layout looks on the right. So you have like your key scheduling algorithm where it takes in one large 64-bit key, and then it kind of breaks it down and does a bunch of like rotations, permutations, things to change it. But it's all like a set of functions that if you have that first key, you're going to be able to get all of the 16 other keys. So that's why really only that first one is important. Just know that in order to make it, a little bit more secure, each one of those F functions is it's going to take in a different key. Then key schedule, or I said key scheduling, but permutations, that's effectively just taking like this really long bit string and then just like jumbling it up. And so then the F function, that has an XOR, has S boxes, which I probably won't get into that much, but basically S boxes take in like a 4-bit or 6-bit input, and then based off of those 6 bits, it kind of maps to a 4-bit output. And then there's also expansion. So expansion is kind of treated as the opposite of the S boxes. So instead of going from 6 down to 4, you're going from 4 to 6 bits. And yeah, so the reason that I actually wanted to do this DES algorithm is for a crypto challenge during the RITSEC CTF. And so I needed to make it so that I knew that I wanted to give them the encrypted ciphertext, and I wanted to give them the key, and then they had to reverse engineer what the actual text was. So it was kind of like a mix between a reverse engineering and cryptography challenge. And so I needed to make it very simple, which actually also made it much easier to implement. So I made it only a 3 rounds of encryption because, hey, who needs all those 16, right? Then I have like the same first or initial and final permutations, but then like my key scheduling F functions are very simplified. So if I compare here versus there, instead of having like the expansions and compressions, I just have permutations. And then for the F function, that's really scaled down. And in order to like actually do what S boxes like need to do, it's very difficult to actually define what every single S box, like what every single input and output is. So I didn't want to deal with all of that. So I was like, why not make it just an XOR? So that's what I did. Yeah.
So did you basically like recreate your own version of the DES encryption, or is it like considered?
Yeah. So the question is, did I make my own version of DES? Effectively, yeah. So I just like made a simplified version of DES because in order to, you could look up online what DES, like what a hardware level implementation of DES looks like. But since I wanted to like force these people for a CTF to actually have to reverse engineer it, I couldn't just use one that was already out there because they could just like copy and paste it into ChatGPT and get the answer, which I know a lot of CTF players do already. I just wanted to try and avoid that. So, yeah. All right, so actually implementing the hardware encryption, everything is a component. So that's why I have so many files. I broke down each area. So there's the F function, like the encryption is like the That's where everything actually comes together. I'll talk about that in a second. There's FP, final permutation, initial permutation, key compression, key generation, and then the K permutation and the round function. And so in each of those components, I was able to like define the functionality for each of them. So say I needed to XOR two inputs, which I think is actually on the next slide. So for the F function, I can just say, hey, I want the output for this component, so the out pin, to just take the two input pins, the F input and sub key, and just XOR both of them together, and then that's the output. And so if I'm able to do that, then I can just treat that as its own component and then like wire it together. So I'll talk about that in a second, actually wiring all of those things together, what it looks like. But if you take like the permutations, this is what I mentioned before about how you need to hard code all of these. Like you can't just have an accessible, like an indexable array, because that's not how hardware does, how hardware works, because you can't access each location of this hardware on the fly. All has to be like physically mounted and built by itself. So it has to be like this standalone thing, and that's why you have to do every input is mapped to specifically one output. And then finally, the rounds function, that's kind of the implementation of it. And that port map at the top is what it's going to start looking like for implementing each of these components. So putting it all together, this is what it looks like. So isn't that fun? You take a bunch of inputs and you map them to the inputs of each function. And so, not function, component, but same difference. And so let's take keygen, for example. If you look up there, there's a port map. And so all of those ones on the left, all of those ones on the left are all of the specific names of each signal within your component, and then all of the ones on the right. So like your key input, that's within the actual component. That's what that physical input for that part is called. And then the key in is the signal from outside the component that is being mapped to that specific component. And then key out 1, key out 2, key out 3, those are all the signals that are leaving that port map. And then if you see down at the rounds function, bottom left there, you can see that the key out 1, key key out 1 is then the sub key for that first rounds function. So, yeah. I got a question. Yeah. Yeah, so what you're seeing up here is VHDL, which is, I don't know why I did it in VHDL. VHDL sucks. If you're planning on ever doing any hardware, do yourself a favor and just use Verilog. Verilog is much more intuitive because it's a lot newer, and so it'll end up just looking like Python versus this where you have to define every single input and output of every single function, and you have to keep track of all of your port mappings, and it's just like a whole pain. But yeah, this is VHDL because I wanted to be mean to the CTF players. So, all right. One of the key differences between like an actual hardware implementation versus a software implementation of these cryptographic algorithms is hardware takes time to propagate, and since it's actually just like power in these signals, that power will fluctuate rapidly as like before you actually settle on an input. So that's called propagation, or before you settle on an output, I mean. And so that's called propagation delays. And so if you see all the way up here, this whole box, that's the output. So that's my test bench ciphertext. Pretty much I'm just testing the algorithm to see what it's going to output for if I take this input, so that plain text and that key, join those together through the algorithm, and then it outputs this ciphertext. I wanted to see like what it would do. And this is like simulating what it would actually look like in the hardware. And so you see for 1,000 picoseconds, to be fair, very, very short amount of time. But this is a real thing to think about when it's actually implemented, because it will likely take more time than that. But during that time where it's all of those red X's, you will get undefined and possibly like wildly varying outputs. So you have to wait for like the propagation delay to like actually complete, so that the plain text in like the key in have actually fully gone through the function, because some areas of like this implementation, some of those bits will reach the end before others, so you're going to get like a very like widely varying output before that propagation delay is fully done. And so that's, if you try to access it before this propagation delay is actually finished, that's what a hold time violation is. So you haven't waited long enough for the output to actually hold, and it's changing rapidly, and it's not actually what you want. So definitely something to keep in mind when you're implementing this. So yeah. Do we have any questions about this before I hand it over to James? All right, cool. Take it away, James.
Thanks, Dan. So for implementing AES and RSA, I didn't just do it because I wanted to. There was actually a purpose to it. Me and one of my good friends, Danny, who's not here at the moment, yeah, the director of PR for the club. You've probably seen him a bunch. But we have a command and control server we've built for the RedSec Red team, which I'm the chief of, and you should definitely come to on Wednesday nights from 6 to 7. So we had our C2, and we built it in with a lot of different languages, and we kind of built it as a fork of a lot of different school projects that we had worked on. So the final project from GSys 127 Tiny Chat, we forked that to create our C2 server. We forked one of the projects from CSEC 201 to be our Windows payload. But the thing is, with all of these, they worked over raw sockets. So it was just the TCP, like we only had layers 0 through 4, and then there was no TLS, there was no encryption, no anything. So when we were using them in our red versus blue competitions, it was really easy to spot our C2 because this traffic was unencrypted. So all someone had to do was open up Wireshark, and they could see the commands being sent from the payload to the server. So we wanted to implement AES and RSA to do the encryption. Why implement both algorithms, you may ask? So AES is a symmetric key cipher like I talked about earlier. So both sides have the same key for encryption and decryption, and they need the same key. Now the problem is, how do you get that key from one side to the other, from who generates it to the other side who doesn't generate? Well, you use an asymmetric encryption to transfer that key. Why don't you just use an asymmetric algorithm to do all the encryption? Because it's really slow and that wouldn't be efficient. So you use an asymmetric encryption algorithm to transport the key, and then use that symmetric key for all of your communication. Unfortunately, this meant I had to implement both algorithms in all 3 languages. And this was easy when I started out with just implementing AES in Java. And then I realized I would have to implement it in C. And I got really sad, but I still did it because it was cool. But it was not fun. Honestly, actually implementing it was easy. This is how AES works. There's a couple different layers. There's an XOR with the key. There's a byte substitution layer, a shift rows, and a mixed comms layer. I'll show you guys how I implemented it. But in actual Java, it was less than 200 lines of code. This is the encrypt function. We have an XOR. With AES, you have a state at all times. So that starts with your plain text. You XOR with your keys. So you have one master key, and this gets, I guess, diluted into your round keys. So depending on what mode of AES you're using, you can have 11, 13, or 15 round keys. So you XOR it with your round key, and then you go through this loop. So I'm in the mode which it'll have 11 round keys. So we have to loop through 9 times. Byte substitution, shift rows, mixed comms, XOR. Repeat, repeat, repeat. It's very simple. You just have to keep track of your state. So this is the XOR function. It's very simple. It's just XORing 2 maps of bits to each other. This is the byte substitution. It's just a really big 2D array. It's quite simple. Shift rows, you are literally taking all of the values and shifting them to a different spot. Quite simple. And then mixed columns, honestly, I don't even remember how this works anymore. This is actually kind of complex because you're doing Galois fields multiplication, and it's even more complex on the inverse when you're doing decryption, because In encryption, you're doing Galois field multiplication times x, x squared, and x cubed. When you're doing decryption, you have to do it times x to the 14th, x to the 13th, x to the 11th, x to the 10th. So that's a little bit complex, but Stack Overflow is there for that. So like that was not the difficult part of doing this. One of the most useful things that I learned doing this project is when you're implementing these types of things, just like going and reading the standard in the RFC, very useful. It can be quite intimidating to look at these documents, but if you just implement it exactly as they state, you'll do it correctly, which I should have done way earlier because I messed up so many times doing the key expansion algorithm before I just read this and did it correctly the second time. Another one, just because it looks like your crypto is working doesn't mean it's actually working. So if we back up all the way to the encryption algorithm, there's a spot right here where we can implement everything correct, like we can implement everything wrong. However, it'll look like everything's happening correctly. Because if we implement it the same way for encryption and decryption, we'll encrypt, have ciphertext, and then we'll decrypt and get our correct plaintext backwards. However, our algorithm is not correctly working. And that can mean that our ciphertext is deterministic, which means that an attacker, if they knew if they knew the algorithm, they would be able to determine they would take the ciphertext and be able to determine the plain text from that because it's deterministic. We do not want this to be deterministic. We don't want someone to be able to see the ciphertext and be able to figure out the plain text. In my case, I had screwed up the key expansion algorithm, which meant that all of the keys that I was generating for my first key were not correct. So you have to go to an example of someone doing it correctly and find out like what should it look like when I enter in the key A. What should all of the round keys generated by that look like? That way you know that your encryption is actually working correctly, because crypto can be a place where it looks like it's being implemented correctly, but it's not actually working correctly. Another good example of this is the hardware encryption for Windows. What's it called? BitLocker, thank you. BitLocker, there was a very similar vulnerability that was found to this about a year and a half ago where it looked like it was actually working. However, there was an implementation issue different than the math that theoretically worked, right? But it's still, yes, it's called a side channel attack. I didn't feel like going into that vocab, but yes, it's called a side channel attack. It's a really cool class. You guys should definitely take it. But those things can happen when you're trying to implement crypto. You can have the math theoretically work when you've written it out on paper, but when you go to implement your code, if you don't do it correctly, it can look like it worked, not look like it worked, and then you have a really big vulnerability like that. All right. This was the most fascinating point of this project and why I really wanted to do this presentation. This was an incredible example of how different programming languages abstract different parts of coding from you. So ASCII are the characters from 0 to 256, and specifically human-readable ASCII, which are all the characters you're all familiar with. Lowercase, uppercase, numbers, special characters, those all exist in ASCII 32 to 127. However, AES operates in Galois field 2 to the 8, which means 0 to 256. But what does this actually mean? It means when you have plain text, it's going to start as a value between 32 and 127. So let's say I have my name James. That's going to map to 94, 48, I don't know what the actual numbers are, but it's going to be in that range 32 to 127. And then after it goes through that AES encryption, all 5 of those characters will now instead be a number within 0 to 256. Shouldn't be an issue, right? So this is, obviously the human readable. So like if my name is James, so it would be 106, 97, 109, and then 2 other ones, right? And then it might map to 186, 18, 223, 105, 14, right? The issue with this is we typically don't work with those characters from 129 to 255 in code. So something I saw for the first time was how every byte out of the normal ASCII range, so before 128, outside of that range, so 128 to 255, is actually prefixed by the byte 0xco. Well, different languages abstract that from you. So when working with Java, you would have no idea. You only actually encounter this problem once you start sending communications from one language to the other, like our C2 server was doing, because our C2 server was written in Java and our payloads were written in Go and C. So we're really confused, like, why are when we send something from our C2 server to our payloads, are there a whole bunch of just COs before everything? Well, that's because C and Go don't abstract this feature from you. They make you actually like read out that 0xCO before your byte character. That's just something that's defined within like ASCII itself. So, if I had just read the standard or the definition for ASCII, I would have known this before spending about a week of debugging it. So this is super cool to see the abstraction of it, because Java completely abstracts all of that from you. Go, it will abstract it from you when you are creating a string. So if I have a value that's 254 and I cast that from a string to a byte, it will automatically add the extra control bytes before that. And so when I send it off the network, Java would completely understand it. However, when Java sent something in and I read it from a byte to a string, it didn't abstract that for me. So I had to manually take out those extra control bytes. And then C doesn't even like have a concept of strings. So obviously it's not going to abstract that from you, because it literally just understands characters. Future work, currently I only have AES codebook mode implemented. There's a whole bunch of modes when you're using these different ciphers, and that is to determine how they should be used. And that's kind of you should choose the mode based on like what scenario you use. Codebook is actually considered insecure. Codebook is considered when you just use your algorithm, your key, and your plain text, because it is like, you would be able to theoretically build a code book for every key, for every plain text. What would the output be? So there are other modes, like Gallo counter mode is the one that's used in TLS. And eventually, I just want to fully implement TLS according to the standard, because that would be really cool. So any questions? Yeah. Great question. Eventually, I want to do product security. I mentioned I work at Apple. I'm in the business security team right now, and eventually I want to work on the product security team. So doing stuff like this was kind of just like an introduction to me in like doing stuff like implementing stuff from a standard, implementing encryption from a standard. I obviously could have just like used it from a library. Yeah, that would have taken maybe an hour to figure out. But I wanted to implement it from scratch because I want to get experience in that. And then you're able to talk about it in interviews like, hey, I implemented AES and RSA in a working product that I use in red teaming. So yeah, that's why. Any other questions? Yeah, well, thank you guys.